Okay, hello, everyone. I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're truly delighted to have Thomas Hubert from Google DeepMind to tell us about AlphaProof. He says it's the first public talk that he's given on AlphaProof. And Thomas started out in quantitative finance, a topic dear to my heart. He was involved in AlphaGo, AlphaZero, MuZero, AlphaTensor, and he's one of the lead authors on AlphaProof. So as always, I will watch the chat, and if you have a question you're not sure about, put it in the chat, and I'll either ask you to ask it or raise it. And we'll have time for questions at the end. So with that, please, Thomas.
Hi, everyone. So I'm really glad to be here and really would like to thank the organizer and Michael for inviting me. It's indeed my first public talk about AlphaProof. And so hopefully I hope this is useful for everyone. So 3.5 years ago, I had just finished 2 big projects. One was AlphaCode and another one was AlphaTensor. And during the Christmas holidays of 2021, I actually stumbled on this talk on YouTube from 2019 called The Future of Mathematics. And what was quite striking was that the comments were extremely positive. One person said, "This is the best lecture and the best YouTube video ever. I've never watched anything more enjoyable." I was very intrigued. What's the future of mathematics? And I pressed play. And so this video started a chain of events that basically takes me here in front of you. In this talk, I really want to focus on the big ideas that allow us to work on AlphaProof and why we believe that it has a really integral role to play in the future of mathematics. So the talk is organized with we'll first talk about the rise of formal mathematics, then about our experience in reinforcement learning and the lessons we took away, and how these two things kind of come together in AlphaProof. So Galileo said, that the laws of nature are written in the language of mathematics, and I find that as quite striking observation, especially since that we've made so much progress since then, and now indeed, just a few equations on a single page can describe with extreme precision how the universe works. In a famous essay, Eugen Wigner, I think it was called The Unreasonable Effectiveness of Mathematics, he argues that mathematics is not only descriptive, but it also has kind of predictive power. And I think one example he gives is about matrix algebra and how it impacted the birth of quantum mechanics. And so, of course, once you can describe and predict the world, you can start to think about shaping it. And if you look around you, all the technology we have, really mathematics is at the core of all of that. I'd like to also argue that maybe mathematics is a root node to intelligence. We like this word root node that Dennis is talking often about. Indeed, mathematics requires reasoning and planning, generalization, abstraction, knowledge and creativity, and is open-ended with unbounded complexity. So that's a lot of keywords, but you'll see them and you'll hear me say them repeatedly during this talk. And over the years, I guess I realized that you also require, mathematics even requires an eye for beauty. It's really there is a part that is really like art. So in summary, right, I think I'm trying to motivate why work on mathematics, but of course, mathematics is a root node to understand the natural world, and it might also be a root node for intelligence. I wanted to go a little bit, really do a really super short history of formalization in mathematics, because mathematics hasn't always looked like the way it looks now. And I think it's the Greeks who basically understood the importance of proofs 500 years before Christ. And basically, can you imagine you find something that will tell you with certainty that you have attained eternal truth, and you can use that method to discover more and more truths about our universe. That must have been, I don't know, extremely exciting. And so proofs is really at the heart of mathematics. But what constitutes a proof has kind of evolved over the millenniums of mathematical history. Maybe we wouldn't consider what, part of what Euclid described in his Elements book as enough rigor for mathematics today. But it's indeed Euclid who started this axiomatic method, which was really developed by Hilbert in the early 20th century, that kind of really led to the mathematics as we know now. Concurrently, really, even though kind of Euclid came up with axioms and the Greeks had this method of proofs a long time ago, for a very long time, actually, I think until really the Renaissance, a lot of mathematics were written completely in words. And so, you have these things like a square and 10 times its root are equal to 39. And that's what we would write now, a square plus 10x equals 39. And how you would solve this was like take the coefficient of the root, divide it into two parts, and multiply one of them by itself, add this to 39, etc., which we now kind of would write very concisely with symbols. And at least there are like two big steps there. First is to represent numbers with their own kind of symbols. And then is to use these constants and kind of, I think it's only with René Descartes in the 17th century that basically algebra looks like kind of what it looks like now, really symbolic, with early alphabet letters for constants and like kind of X, Y, Z to describe unknowns. So I think it's not hard to argue that this movement, for instance, precise notation and axiomatization really eliminated a lot of ambiguities and logical error, and that symbolic notation made it much easier to manipulate complex manipulations. It's much more tractable. It requires much less cognitive load, right? You don't have to read the whole text. You can just see minus b over 2 plus or minus square root, etc. for the formula. And it packs information extremely densely. I don't know if it's a joke, but I heard someone say that maybe Einstein's biggest contribution is Einstein's notation. Maybe that's a bit excessive given the impact of general relativity, but it certainly had it was certainly extremely important. And then once you have symbols and then you can pack information densely like this, you can start to lift yourself from examples, and you see common patterns across different contexts. That abstraction and generalization, you can unify different areas of mathematics, and even led to create new fields of mathematics. I think the example I like the most there is the discovery of non-Euclidean geometry, where people are trying to get rid of the fifth axiom and realize that actually, if you try to get rid of this, then you can discover new geometries, in particular Riemannian geometry, again, that led to general relativity. That was extremely important in general relativity. So really, this movement of formalization are extremely important for mathematics, but also beyond mathematics. And of course, one of the biggest clients is physics. And so I believe that computer formalization is basically just the next logical phase in this grand arc of mathematical formalism. And what does that mean is basically using code to write mathematics. And so there's been quite a few languages to describe mathematical reasoning. And so not only mathematical computing, but mathematical reasoning, and such as Koch and Isabelle. Today, I want to talk about Lean. So Lean is one of the most recent ones, originally developed, I believe, for software verification, but also with mathematics in mind. And when mathematicians saw Lean, I think they saw in that there the tool that will make the next big step in mathematical formalism. And I think what is really cool about Lean is it has like a really vibrant open source community of mathematicians. It has been used to really formalize actually cutting edge mathematics, fields middle level mathematics. And there is this huge quest of the community to build basically the math library of the future. And so that library is called Mathlib. It's built open source on basically the free time of mathematicians. They do it for free out of really passion and belief for this project. Mathlib aims to be general and unified. So general, it means that it tries to have really the weakest assumptions and the strongest results. And unified, it means that you are going to try to find one definition per concept. And that's actually not really true in informal mathematics. You may have like many papers that basically talk about the same concept, but they define it slightly differently. And actually, they might not be compatible with each other. And so kind of finding kind of that abstraction that kind of underlies those concepts is actually one of the biggest part of building Mathlib, building those definitions. So Mathlib covers about 80% of the undergrad curriculum, I'm told. But most of the library is above undergraduate, but it has a lot of holes. And so, for instance, I think a notable hole in Mathlib is complex analysis. Another one is the theory of PDEs, etc. But as you know, like this graphic shows, you can see it's like kind of one monolithic library where everything is connected together. And this is very important to represent modern math, where more and more things are connected. I think that the Abel Prize yesterday was given, for instance, for someone who was studying algebraic analysis, and things like, for instance, the Lang program is about basically connecting all of math. So to be able to connect all of these is like a crucial feature for modern math. So computer formalization really unlocks enormous synergies because of two things. First is that it gives you perfect verification of proofs. And the second thing is that because we use code, it gives you access to all the tools that are developed for software. And so the instant wins are, well, your kind of correctness concerns disappear. You can trust giant proofs. And really proof checking is entirely delegated to the computer. And so maybe I would note there that it's not like all mathematicians are actually concerned about correctness, or at least correctness of the current system of how mathematics is done. I think in most areas of math, actually, there are not so much concerns for correctness, and actually some might really have, where the objects become really abstract and difficult to keep everything in your head, then there might be some concern about correctness. But these are like kind of have knock-on effects for potential things that I see are potential game changers. The first one is quite funny, is that it transforms mathematics into a video game. So I think that's what Kevin Bezant likes to say, but I think that's a really like kind of a game changer. And the first reason is that, so this video game, what does it look like, right? You have levels, which are basically the theorems you need to prove. You can interact with mathematics. It gives you a signal for being right, for having done the right thing. You always have harder level, and like maybe differently from other video games, it's actually super meaningful and useful and profound. You are just adding new truth, new eternal truth, right, to the library. So really cool game, and it has kind of impact obviously for education, because if you are doing something that you find fun, and then you are just going to very, very easily learn it. Of course, now kids, they just love software. If it's fun, you're going to just learn, and you have like I want to even give an example of my dad, who was trying to learn Galois theory in an online massive online class, and he did week 1, week 2, week 3, and at some point he couldn't tell if he had understood the concept well or not. And he couldn't make progress anymore. And so he tried to get feedback from the teacher, but unfortunately the teacher was not answering. And so basically he got stuck. And so, if you can get feedback directly from the machine, from the computer, and you don't have to go to, the one teacher that knows about it, then basically you can make progress on your own, and potentially anything is possible. You can also, of course, create software that basically lets you, see the detail that you want as a reader rather than, as the author. Maybe, some mathematics have a bad tendency to say this is a trivial step. Maybe it's trivial for you, but for the person who is going to read your paper, it might be really not trivial at all, and you might not know how to proceed. After that, of course, you unlock all the tools that were developed for software engineering, for math. And that plays a big role, I think, in unlocking massive collaboration. And so that's kind of a point that I learned from talks that Tertao gave, and that really struck with me. And he's saying basically, it's difficult in mathematics to have huge collaborations. And if you look at papers, they are often like single author paper, 2 author papers, and maybe maximum 5 author paper. And the reason why is that basically you would need to check what everyone else is doing. because mathematics is about being 100% correct, right? And so if you can't tell whether like the 1/4 of the paper is correct or not, then that's not good enough. But if you could rely on, say, Lean to check the work of everyone, that all the proofs are correct, all the arguments are logical and make sense, and actually prove what you said it's going to prove, then suddenly you can do massive collaboration, right? And you could collaborate with thousands of people you've never met, that live maybe in the middle of nowhere, and they just contributed a little bit to your work, and the system is checking, yes, this is correct, you can trust it, and that's all you need. And you can see this actually, I think MathLib is one of such projects where you have hundreds of mathematicians contributing to building this library of the future. They use tools such as GitHub, and they were developed, for software engineers to work asynchronously, and so software engineers have been doing this for a long time, open source. And I think, if I understood correctly, one of Terry's idea is to use this to do new math as well, not only formalizing old math, but actually to do new math and maybe solve new problems. Can you scale humans in mathematics? And so that's a way to do it. So it has all these great things for it, but the reality is that only 0.1% or 1% of mathematicians have adopted Lean, and there's definitely challenges to computer formalization. And I think the main reason why is that it's just not yet a good tool for mainstream research. It has a fairly steep learning curve, like in most programming languages. It's a significant time investment as well, because to get perfect verification, you need to write down all the details. And so, that might be not necessarily exactly what you want to do as a researcher. Like, this is true. You may not want to have to write down all the details at excruciating level sometimes. The library, as I said, has quite a few gaps, and could use with more automation, especially to limit the time investment. And maybe a big thing as well is that like maybe the benefits are not yet understood very well, and there is a perception that is not necessary for research at the moment, which might be true. So I want to give you a little bit of an example of actually what Lean looks like, one level in this video game. And I hope you can see it. Is the proof of the fact that there is infinite number of primes. And so here you can see the theorem statement. And it's, like, remarkably, it's almost what you would write on paper. For all n, there is a p that is bigger than n, and that is prime, and that's the way you prove that there is an infinite number of primes. That's the proof. You may actually be able to understand some of it, and we may go through it, even if you have never seen any Lean, because it's a language-based high-level syntax that is mirroring normal mathematics. So let's go actually a little bit over it. So there is this first line that says, let p equal mean fact of n factorial plus 1. And so, of course, if you know Euclid's proof, you see that mean fact is just the mean factor of n factorial plus 1. And I want to draw your attention to the right, where there is this thing called the tactic state, which basically says what we know of. So what we know is that n is a natural number, p is a natural number, and it's the mean factor of n factorial plus 1. And it tells you what you have to prove. You have to prove that there exists a p such that p bigger than n and p is prime. And so the next line says, oh, now let's prove that n factorial plus 1 is not 1. And you see there's a proof just after 1. And so you see in your tactic state, now you have access to this new fact that n factorial plus 1 is not 1. That's like a fairly trivial fact. And maybe that's already too many characters to prove that. But anyway, next line, you say, now I can prove that p is prime. Let's prove that p is prime. And then there you can use a theorem that says, well, the minimum factor of a number, if it's not 1, is going to be prime. And now you know that p is prime. And then you continue like this, and you can complete the proof. And at the end, you should see no Gauss. And so it used to be that in an old version of Lean, you would receive this little tada kind of emoticon, and really get some kind of nice little buzz. I think it has unfortunately disappeared from the new version of Lean, but hopefully I conveyed that there is a huge enthusiasm from a vibrant community of mathematicians on pushing this next stage of formalism. And personally, I believe that basically formal math will have an integral role to play in the future of mathematics. It's kind of inevitable, just like kind of code or software is the world. But now I want to talk about some concurrent development in AI, in machine intelligence, and focus on something that was extremely popular a few years ago, got forgotten a bit with the advent of large language models, but now is making a comeback big time. What I want to talk about is, I hope you understood with my video game and my buzz, kind of the link to it is reinforcement learning, also known kind of as RL. So what's RL? So basically RL is a very, very general framework of an agent trying to achieve a goal. It's really about trial and error learning. And you have this agent that learns by interacting with an environment to maximize the reward. And there's often kind of a misunderstanding about kind of that reward. The way to understand it in its generality is basically a goal. And so that reward can be extremely sparse. It can be 0 all the time and 1 when you achieve the goal. And so maybe what is important in RL is that you're really trying to achieve a goal. If you don't have a goal, then maybe it's not RL. And so, this RL run at scale has proven, many times now that this was a road to superintelligence. And so I've picked some sample of the most successful stories coming from DeepMind of running RL at scale. And as you can see, there's a lot of examples of games and video games, like the similar work on Atari or the work on Go and StarCraft and Stratico. But it's not confined to games. It's really about an agent trying to achieve goal. And so it was used to discover new algorithms in AlphaDev and AlphaTensor. But it was also used to control plasma in a tokamak to improve the reaction of nuclear fusion. So after those things, I want to focus on, well, I guess the work that I had really the chance to be involved in, called the Zero series that starts with AlphaGo. But especially from AlphaGo Zero, basically, we showed that we could train an agent to master domains. And really, when I say master, is actually really be world champion, unbeatable level at the time, without any human input, information, basically learning from scratch. And so that's what I call the zero philosophy. And so I want to remind you what is the zero philosophy. And it says this, it's like if an agent can learn to master an environment tabula rasa, then you demonstrably have a system that is discovering and learning new knowledge by itself. It's all about knowledge discovery. And knowledge discovery is something we've forgotten a little bit. We basically, for the last couple of years, we've been really good at ingesting kind of human knowledge, and that has like incredible kind of, it works incredibly well. But we've lost a little bit this idea of discovering new knowledge. And basically the work that I presented to you is really did that. If you can do this also tabula rasa, it means that you may have something that is quite general and that should apply to other domains. And so this tabula rasa thing, I think it's really good for research, right? Like from a research perspective, I think it's hard to argue that if you input zero knowledge in the system, it discovers all human knowledge that took thousands of years to be discovered, then it must be doing something really interesting and really doing knowledge discovery. And I think this property is particularly important to advanced science, because a big part of doing science is to advance knowledge and explore areas that are not yet well understood. You don't have data for that. You actually need to create the data. You need to accumulate knowledge and continuously generate new knowledge and new interesting truths. So just some case studies, AlphaGo Zero and AlphaZero, as I said, they learn simply by playing against themselves, starting completely from random play. And they rediscovered in both cases, human patterns that took thousands of years to be discovered by humans in just a matter of days. And ultimately, for some of those patterns, they were discarded in preference of new discoveries that humans didn't even know about. And so for sure, at least the game of Go that I know very, very well has completely changed after seeing the new rules that were proposed by AlphaGo and AlphaGo Zero. And I believe it's the same for chess. And so here we just have some figures about the frequency of those patterns during the course of AlphaZero training. And so, for instance, in chess, you see that maybe after 2 hours of training, basically discovers this Caro-Kann defense. And it plays it quite a while, with quite high frequency for a while. And at some point, probably discovers like some counter, and that kind of stops playing it. Where maybe the Queen Gambit, at least for the 8 hours that AlphaZero was trained for, like kept being more and more played. And so I want to say this not only for board games. In the work we did in AlphaTensor, AlphaTensor was able to discover novel kind of algorithms for the fundamental task of matrix multiplication. So this matrix multiplication has been studied like quite a lot in the last 40, 50 years, but still we could discover new algorithms. As a bonus, that's also a work in which we show that we could do this discovery while tackling a huge action space, like for practical matters that is kind of infinite. So in all those examples, I think we showed that for a specific task, we could actually discover new knowledge. Under the hood, we have the same algorithm running. And maybe a good question is there an environment that kind of captures a much broader class of tasks relevant for science? And as you may guess, our answer is yes, it's mathematics. But just before we get there, I want to touch a little bit on kind of what I think made those systems basically superhuman. The first one is scaled up trial and error. I think that's extremely important, especially when you get grounded feedback signal. Because once you basically venture, out of what's known, you need a way to ground yourself and to measure that if you're achieving your goals or not. The two other things that I think are quite important as well is search and self-play. So search is I think really accelerate the discovery of new paths and skills. And kind of one example that we like to highlight is Move 37. It had a very low probability of being played, but by exploring it, the system discovered that that was actually a really interesting idea. And so that's like kind of how creativity comes. Maybe creativity comes with search a little bit. And for self-play, always having the right opponent to play against in Go was really, really important. And so let's map that. How can we do scaled up trial and error in math? Well, we use Lean that gives us an environment to really explore mathematics completely in silico. And then we use that with the AlphaZero algorithm. We get grounded feedback signal from Lean. It will tell us if the proof we've written is correct or not. Search, we just basically use what AlphaZero has, what works in AlphaZero. And maybe one question that is left is, what is the equivalent of self-play in mathematics? And so you understood, right? Like that's how the two comes together. AlphaZero for mathematics makes a lot of sense for us to go through kind of formal math. And so let me say it again. Basically, what is the master plan? One, Lean gives us the way to do scale-up trial and error with an environment to explore mathematics completely in silico and a perfect feedback signal for proving. And so if we extrapolate from our previous work on Go, chess, tensor decomposition, discovering algorithms for code, etc., we extrapolate and say we can therefore reach superhuman intelligence and discover new truths, just like in Go and chess, etc., provided two things: we can generate high enough quality quantity of problems, and RL works. So, I guess my work influences me, but I'm like pretty sure RL works. But then the question that is remaining, that is related to the previous question of self-play, is how can we generate high enough quality and quantity of problems? And so where do the problems come from? In the video games, where do the levels come from? I think the first answer has to be that humans define the problems. And why is that? It's because basically we want to help human mathematics. We could invent a brand new mathematics, but if no one reads it, maybe it's less impactful. And also, there are already a lot of problems that humans find interesting and humans have defined for us. So why not tap into that, right? But the second answer, and a complementary answer, is that AlphaProof also defines the problems. And there are two ways to do this. One is around human mathematics, and another one is, I guess, beyond human mathematics. And so ideally, especially in the second point, it would mean, that it can discover new areas of mathematics, build new theories that are interesting, etc. And so I will illustrate a little bit what, around human mathematics looks like. But before we move on there, I want to take a step back, especially if we are thinking about AI for mathematics. Because if you want to do mathematics, there is definitely, a choice you can do at the beginning, whether to work on informal mathematics or on formal mathematics. So I've kind of tried to show a little bit, that kind of the pros and cons from maybe a mathematician point of view first. And now that's from an AI kind of perspective now. Um, and by the way, like most effort in AI is actually on informal mathematics. And why is that? Is because all the data that is, in mathematics by many orders of magnitude has been written in natural language. And so you have directly accessible a large amount of data. In comparison, even though, there is like kind of an absolutely amazing effort in building MathLib, in comparison, it's still a very small amount of data that exists in informal language. However, as I said before, the trade-off you have is that if you use formal mathematics, then what you do is the reasoning becomes verifiable, while that's not the case in informal mathematics. And I guess I believe that if really your goal is to build a system that can go beyond humans, and that's a property that called the verifiability property. You can, of course, improve the reliability of the system, the formal systems. But one problem in math is that if you have any false statements in the middle of your tower, then the whole thing is ruined. You really need to have close to 100%, really close to 100% reliability if you want to do anything meaningful. And so AlphaProof's kind of foundational bet is that perfect verification will, in the long run, be the most important property for mathematics, especially if you want to go all the way. And I say that for mathematics, but I believe this is also true for many important impactful applications that we cannot solve. Almost by definitions, like if we can't solve the problems, it means that probably we don't have a really good understanding of the problem, and we don't have much data that we can rely on. If it's a brand new area, then there is no data about it, and so you really need a process that can kind of accumulate information and accumulate true information that you can kind of verify and build upon, and kind of continuously build this kind of I don't know, this pyramid of knowledge. All right. So until now, let's just recap. I guess I've shared with you that in certain domains we've already built superhuman intelligence, and we know the way to get there. And they had some properties, and the algorithm had the property that they could really discover new knowledge. I highlighted the importance of trial and error with grounded feedback. And so I hope it's clear why kind of these two things why kind of we use formal math. And it's because it's our ambition to go all the way. But before we kind of really go all the way, we had a milestone in mind from the very beginning of the project. And the milestone was to participate at the IMO, the International Math Olympiads. So, okay, what's the IMO? So the IMO is basically the world championship level in mathematics for young minds, and they gather like the best minds around the world, right? So every country brings their top 6 high school students, and they try to solve 6 problems. There are 2 that are easy, 2 that are medium, 2 are hard, and they have 2 4.5 sessions per day. So you have 9 hours to solve 6 problems. And so let me try to illustrate what it looks like to pick 6 high school students for the USA. So I estimate there is about 17 million high school students in the USA. And obviously not every kid loves doing math or doing math competition. They might instead play video games or, hopefully build the math library of the future. Jokes aside, I guess, there is about 60,000 of them that participate in these AMC competitions. That's a factor of 300, which is, quite reasonable. If you do well there at the AMC and you're still motivated, you get to do the AIME competition. And for those of you who have been following a little bit kind of the benchmarks that have been kind of reported in AI recently, you will see that there is this famous math benchmark that basically contains a lot of AMC and AIME problems. And so these are favored because, especially in the AME, you have to give an answer that is an integer between 1 and 1,000. And that's how you rate those models. It's like, did they guess the right number? It doesn't matter if the reasoning is wrong. Did they guess 177? And it's still fairly impressive because obviously it's more likely that with good reasoning, you make the right guess, right? Anyway, if you're really good at the AME, you get to participate at the USA Math Olympiad, and then you would want to qualify for the IMO camp and to finally make the last 6. So there is about 6-7 orders of magnitude there. And when I talked to a colleague who did the Olympiads for the UK, he said that they train for thousands of hours for this competition, maybe on average 3 hours a day for 3 years. So incredible amount of preparation. Now let's talk about the IMO problems. And I have this quote from Law. So who is Law? He used to be the national coach for the USA for the last 10 years. And he starts with this. He says, I tried this year's problem while at the IMO myself. And it took me hours. I don't know if you see that well, actually. He talks a little bit about the problem, context about the IMO. Problem are specifically selected to be non-standard. And during the IMO itself, national coaches meet to pick the problem to appear on the exam. And one of the most important tasks is to avoid problems similar to problems that appeared anywhere before. And they would dig up some old obscure math contests and show it to the group, after which the proposed problem would be struck down. And so, like the IMO really, as a competition, really aims to test reasoning rather than knowledge. It takes hours, even for specialists or, like for our most brilliant mathematicians. And importantly for us, the problems are not leaked. So we don't know what the problems are going to be. And we thought this is going to be a real test of reasoning. I said before, there are like 2 easy problems, 2 medium problems, and 2 hard problems. The easy problems are actually incredibly hard already, and only half of the participants can solve 2 or less problems, 2 or more problems. All right, so we come, is the IMO 2024, that's the one we want to participate in, the 16th and 17th of July. And so first, I want to be clear about our participation. And I think the way to think about it is more like kind of an Apollo program. And our goal was, can we reach the moon? In a sense, can our system solve the 2024 IMO problems at all? Given the compute that, is available to us within our group at Google DeepMind and with a reasonable amount of time. So I want to take you a little bit through kind of some events before the IMO. So in January 2024, we're 7 months away. We are like, this is the year, but we really need to make a decision about geometry. And so what's happening about geometry? The problem is that MATLAB is extremely sparse for 2D Euclidean geometry. So it's missing a lot of the results we would need for the IMO. Like I said, the knowledge that is required for the IMO is really small, but you still need some knowledge, some theorems about inscribed circles, etc., etc. And so all of this doesn't exist in MATLAB because, for research math, it's not that interesting. And so we are like, should we fill that knowledge ourselves? What should we do? And kind of miraculously, another group within Google DeepMind had been working on exactly the IMO geometry problem. And their system was already very, very strong, actually close to gold medalist performance. And we only learned about it because they kind of actually wrote a paper and came out in January 2024. So extreme kind of good luck and coincidence. But obviously we decided to join forces for July. And the plan is for alpha geometry to tackle the geometry problems. And AlphaProof will tackle algebra, number theory, and combinatorics problems. A bit later in the year, we have another thing we are thinking about. So we've been training AlphaProof on proving theorems, but not all questions are the form like prove that blah. In fact, at least maybe close to half of the problems require an answer to be determined. Find all x such that this property holds. And so it might not be apparent immediately, but one issue is that that's not obvious how to deal that in kind of formal theorem prover, because if the system says to the question, find all x such that property holds, it says, is the set of x that has this property? then suddenly you have a very easy problem to solve. But that's not the problem that kind of the competition wanted you to solve. And so we debate over what we should do. And there is like the easy mode where we give the correct answer to the model and we ask AlphaProof to prove it. And there is the hard mode where we also try to guess the answer and we prove that it's correct. And so we understand very quickly that we need to do hard mode, even though like for the IMO, the difficulty is really improving rather than guessing the answer. And so we decide to use Gemini to generate candidates. That's how it's actually trained for mathematics. So it's kind of a great fit. And after that, AlphaProof will attempt to prove and disprove all the candidates that Gemini comes up with. Final thing to debate is what should be the input to the system. So should it be kind of the natural language description of the problem, just like kind of humans receive? And actually, you can receive it in the language you like. You can receive it in English, or maybe you can receive it in Chinese. That's all fine, but unfortunately, you cannot choose to receive it in Lean. And so we have this choice of should we do it from natural language, or do we accept that the system will be fed a manually formalized description of the problem? So we discussed this with our judges, Tim Gowers, Joseph Myers, and we agree. We both have we all have the same feeling, is that what we really care about is mathematical reasoning, and so maybe this translation to formal language is not important for what we want to try to achieve. So we decide to give the system the formalized problems as input, and we will ask our internal Lean experts to manually formalize the problems for the system. And so here we arrive like pretty close to the competition, and we are rehearsing a little bit our protocol. So we have an agreement that we will officially receive the problems at 1 p.m. Then our Lean experts will manually formalize the problem. We'll generate 100 of answers candidates with Gemini, and then we'll get AlphaProof to disprove within minutes, whatever it can disprove out of those 100 candidates. Then we'll take the remaining candidates and we'll run test time around. So I haven't told you what is test time around, but I'm going to tell you don't worry.
Thomas,
yes.
Do you give Gemini the formal version or the natural language version or both?
In this case, we gave it the natural language version.
Okay, thanks.
All right, so we arrived the day of the IMO. At 1 p.m., we received a problem. P1 is an algebra problem, P2 is a number theory problem, and P3 is a combinatorics. And P1 and P2 requires an answer to be determined. And so I've shown a screenshot of what the problems look like. So the way I feel is, it's too bad we don't have any geometry problem because alpha geometry is extremely strong. But at the same time, it's an AlphaProof day. All the problems are for AlphaProof. And it's exciting. Let's see what we can do. So obviously, the first thing we do is we have our problems formalized, Gemini generate answers, and then we get AlphaProof to disprove these answers. And what we see is that AlphaProof can disprove like 99% of the guesses within minutes for both problems P1 and P2. And that's really, really cool. We're really happy to see that because we know that on problems that AlphaProof has a good handle on, then it will be able to make a lot of progress in disproving kind of easy cases. So it's a sign that P1 and P2 are actually within reach. On the second day, we received the problems. We already know that P4 and P5 has to be geometry and combinatorics because of how it works, and you have to have easy and medium problems in all categories. So we're not really surprised by that. But we are secretly very happy that P6 is an algebra functional equation problem, because we know that actually AlphaProof is one of its strongest subjects. So P6 is in the hard problems category, extremely hard to solve. But if we may have a chance. And so again, P5 and P6 require an answer to be determined. And what we saw is that the alpha geometry problem solves the P4 problem in seconds. It really did extremely well there. The P5 combinatorics, the story is that actually our Lean expert failed to formalize the problem on the day. It was really not adapted. There was a lot of things missing from kind of MathLib, etc., to represent these kind of problems. It took them a lot of effort to formalize the problem. So on that day, we can't do anything on the P5 combinatorics. And on the P6 algebra, we generate a bunch of cases, and kind of AlphaProof can disprove 7% of the guesses. So it's not 99% like P1 and P2, but it's not 0% either. So it knows something about the problem, can do something. All right. On the next day, we haven't yet proved anything, but we have a way to track progress. And what we observe is that actually AlphaProof has made partial progress on several problems. So on P1, we believe that AlphaProof already has solved half of the problem. So that problem is about, you can case actually the human solution is about casing kind of that number to be either even or odd. And actually that's exactly what AlphaProof had kind of considered, and it could prove one of the branches. And had also done another casing where it said, is this number rational or irrational? It had also proved half of the branch there. And so we are like fairly certain that we had solved like half of the problem. On P2, actually, it looks like, arguably we have already solved the whole problem. And in the IMO, there is this kind of phase, it's a bit funny, it's a phase of negotiation between your team lead and the judges about whether, like kind of what the student has done is indeed, had all the right ideas, is indeed a foolproof for the thing or not. So we didn't really have that kind of phase, but looking at it, it looks like, we could argue for maybe a foolproof there. That's not, that will be within the rules of the IMO, but let's say 6 out of 7 points. And P3, the combinatorics hard problem, as far as we can tell, we haven't made any progress. On the day 2, as I said, alpha geometry had already solved it in seconds. P5, we had made no progress on it. The P6, we saw that AlphaProof actually proved a special case. That is an important special case, and that would be worth 2 out of 7 points. And so we actually know that we are making progress, and that even though we haven't solved anything really yet, we have something like 18 out of 42 points. But the next day, we receive a mail. We receive a mail from our system. And the system has been launched by my colleague Rishi, and that's why it looks like it comes from Rishi, but you see Meta Rishi AlphaProof agent that sends us a mail and says, I have discovered a truly marvelous proof for IMO 2024 P6, but this email is too short to contain. Obviously, it's a joke, and kind of the proof is actually there in the email. And so we're extremely excited because P6 is the hardest problem. We weren't sure, and then it looks like AlphaProof has solved it. So I run to my colleague's desk, Oliver Nash, Lean expert, and so he copy pasted it into Lean, kind of an official version of Lean, and then it all checks. And so I run back to my desk, and without thinking, I forward the mail to Demis and Sergey. That's Demis Hassabis and Sergey Brin. And I just want to share this story because, I think it illustrates kind of the trust I have in this thing. Right? If it was wrong, then I would have really made a fool of myself. But I don't think too much about it. I just forward it without context to Demis and Sergey, who was following a little bit this project. I think a little bit about it afterwards, like maybe I did something a bit stupid, but I'm like, it's okay. I think I'm in a company where this kind of thing is actually cool. So I don't worry too much about it. We're like very happy. And then kind of a proof of P2 comes the same day, a little bit later, a full proof. We have nothing to argue, exactly the proof we wanted. And then we actually managed to prove P1 as well. Another mail on that day. So on Friday, we had everything. So the final result is that P1, P2, and P6 were fully solved by AlphaProof and checked by Lean, no arguing needed. P4 was fully solved by alpha geometry. The reality is that we actually kept running over the weekend in the hope of getting 1 point on P3 because the agent had made some progress. It had proved something non-trivial, but actually, unfortunately, that was not enough for any partial point. So, we reached the score of a silver medalist and missed the gold threshold by 1 point. That's why in particular we're interested by this potential extra point on P3. But I want to make sure, it's obviously with more time and more compute than what the human participants had. I want to come back a little bit on P6 because it was arguably one of the hardest problems in the last 10 years of the IMO if you look at the solved statistics over the years. And so this year, only 5 students out of 600 solved that problem fully. And maybe what was quite incredible is that Timothy Gauss, who is a fields medalist and IMO gold medalist. I think he got a perfect score when he participated. He said that he spent a couple of hours, maybe not, full concentration on this problem, but I did not solve it. And I find the fact that the program can come up with somewhat complicated construction like this very impressive. And so obviously, I'm not saying at all that we are at the level of Timothy Gauss. We are very far from that. But still, we took this as a very encouraging sign for the future that we can do something that is really, really non-trivial. There was a few challenges, reflecting on the method. First is that is obviously the gaps in math So for instance, the geometry gap is the biggest gap. Like it would have been hard for us to do geometry just because that doesn't exist at all in MathLib, unless we would have written that ourselves in MathLib, which would have been possible. And even for P1, actually, I said that we solved half of the problem fairly quickly. And there was one case where I had to prove that it was either rational or irrational. And we were wondering why I couldn't solve the irrational case. And it turns out that a natural way to do it would be to invoke a certain theorem, but unfortunately the theorem doesn't exist in MathLib. It hadn't been added yet to MathLib. And so it wouldn't have, in principle, AlphaProof could have conjectured that theorem, proved it, and used it in its proof of P1, but it's made the problem much harder than should have been. Also, combinatorics problems were really difficult. P5 was extremely difficult to formalize, and in the end, we did not make progress on both the combinatorics problems, P3 and P5. And finally, just to remind, we use many orders of magnitude more compute than human contestants. And so in some sense, we achieved our goal. We successfully landed on the moon. That's what we wanted to do. But maybe next time, we want to make the trip much more efficient. So let me now go into the methods a little bit more. And before I go there, I want to remind you maybe the two important aspects we need to keep in mind. First is that where do the problems come from? And second is how do we prove them? So we have a first model called the formalizer model. It takes a problem in describing natural language as an input, and is going to try to output a lean formalization of it. Okay, so that's how we're going to, basically, we have decided to translate kind of human known problems into lean. So really lean onto the fact that humans have already come up with many, many problems. Then we have another model, which is the prover model. And that one is basically takes a lean state as an input, and it's going to try to come up with tactics, or lines of proofs that might be useful to consider next. We put this prover model into the AlphaZero search. And so here, instead of having a board, Go game board and kind of coming up with Go actions, we have like kind of the current state we are in, like what do we need, what do we know, what do we need to prove, and we're going to kind of search over possible kind of lean tactics or proof steps in this search. And so the search is going to exploit the high prior and high value paths that basically what the neural network thinks. But it's also going to explore low visited path. And so that's exactly the same recipe we had for chess and Go and AlphaTensor, etc., etc. So now let me go into kind of the steps. So step one, you do auto-formalization. You train a formalization model and basically try to auto-formalize human-created problems. And I want to give you a visualization of this. So you have the human problem in the middle, and then you're going to have translation. The translations are going to be approximate. Hopefully, if you do a great job, you'll be able to perfectly translate the problem. But it's not too bad if you're a bit approximate. And that's a little bit what I meant around human mathematics. And that's a big advantage you have in formal language, is that all the statements that you're going to generate, they are going to be checked for syntax. And what that means that have correct syntax is that basically it's a question that makes sense. It's a question that will be either true or false. It's not kind of a nonsensical thing that you can't answer. And so these translations, a lot of them might not be interesting. They might be trivially true, trivially false, but they are all guaranteed to be either true or false. And so hopefully the job of the auto-formalization is to kind of generate interesting translations of the problem. And so you take that. We had a corpus of about 1 million informal problems. we passed them through the formalizer model. And for each one of those, we had like about 100 different translations of that object. So that little bubble of, approximate representation of that theorem, but kind of very precise thing in the end. Now it's about training the prover model now. And so first, you really want to start with something that can do something. And so, we start with a pre-trained model, but the real very first step for us is to build on top of the amazing work that's been done for Mathlib. And we're going to train the prover model supervised on Mathlib. So Mathlib contains about 100,000 definitions, 200,000 theorems, and 300,000 lines of code. With modern kind of AI techniques, you can consume that in a matter of minutes. But it's really a good prior of actions to take. And so basically, you put yourself into a human proof. What is the lean state? You look at what is the next line in the human proof, and you train the model to predict that. And once you have that, you have a model that can do some lean. It's completely out of distribution for the IMO, but it can do some lean, and actually might do actually some interesting things in research math, because basically it's been trained on kind of research math data. But then starts kind of the big step, the AlphaZero reinforcement learning training step. And so here you are going to train the prover model by ARA. And so for each formal problem, those 100 million one, you're going to try to generate experience of proving or disproving, by searching over lean steps. Then you're going to use lean to verify the proofs. And so you'll know, this is a correct proof for that problem. And you're going to reinforce the prover network with each success. And so basically what we see is that AlphaProof first kind of solve the easy one, and then kind of gradually learns from the easy ones, is able to tackle the medium ones, and then all the way up to IMO level. And the final step is test time error. And so there you want to train the prover model on specific problems, again by ARA, the same technique. And here you want to have this because, as I alluded before, even like the greatest neural networks on math, like Tim Gauss, Terry Tao, or people like, the USA team coach have been thinking about IMO for a long time. They need hours to solve those problems. And why is that? Is because, they have to learn something about those problems. They have to think of experiments, what could be true, be false, run the experiments, try to prove or disprove them, and learn something. And so the way that we do this is for AlphaProof to generate variants of the problem that we want to solve. And so I try to illustrate this like this. You first have like on the left a bubble of things that it's this, I don't know, a super high dimensional cut of what it looks like to have an agent that can do this for a very hard problem. There's like the agent can do some stuff, and the very hard problem is beyond what it can do. And so the first thing is we kind of explode that problem with many variants. And if you can do this well, then you may kind of have generated a variant that is one of the things that your agent can already do. And so you may solve that one, learn from proving that, and suddenly you kind of expand your capabilities a little bit in the direction of what you need to do for that problem. And basically you repeat that process. Until you can reach this very hard problem. So let me finish this section with some challenges of AlphaProof. And so one of the challenges is that we inherit from formal mathematics is that obviously most of human data is in natural language. And so the way we've tried to tackle that is with auto-formalization of human data. And I think it was relatively, it is really hard, but basically here we could assume that we had all the knowledge and just kind of formalize statements. The other thing, and maybe the bigger challenge, is that we cannot easily learn and work on areas that are not supported by Mathlib. So if the objects are not defined, maybe it will be very hard for us to, for instance, there's nothing we can say about the Langlands program. There's like so many things that are missing from Mathlib. And generally, I think in a very interesting direction that I alluded to with the self-play and where the problems come from, is that creative building of new objects and theories, the interestingness and the beauty in mathematics is still quite a challenge on how to really make progress on that. I think to have a position on that though is that kind of interestingness is quite subjective. And so if we want to impact kind of human mathematics, I think we'll have to measure it based on kind of human standards. I like to have this thought process, a thought experiment about aliens that have their own mass. And I imagine that, there will be a certain part that is will have discovered the same mass because it's useful, for instance, to predict our universe. But they might find interesting some completely other part of mass that we don't know about it. We might even think that's not interesting. But basically, my position has been that maybe we can use all the problems humans have defined that they find interesting to ground this part. Because basically, in order to solve a really hard problem, I believe you will need to do this kind of theory building and discover new facts, etc. And so, to take kind of the crazy example of the Riemann hypothesis, like for sure, you will need to discover new areas of mass if you want to make progress on the Riemann hypothesis. And so if we basically use, like maybe we can use those problems that are defined by humans to kind of start to understand, to let kind of interesting emerge. If we can prove something about the Riemann hypothesis and make progress there, certainly we'll have done something interesting. And another obvious exciting direction today is that LLMs might be able to learn what humans have found interesting and help in this process. I see I'm a bit out of time, but I only have 3 slides left. Pretty short. So what's next? So what's next for AlphaProof? As I said, the IMO is just a milestone, and we have ambition to go all the way. So what we need to do now is to broaden AlphaProof to the entire mathematical landscape. We don't want to be stuck at high school level math. We'd really love if we could contribute to the frontiers of research math and make AlphaProof as a useful tool for every thinker. So, going back to the understanding of the importance of proofs from the Greeks, if we could democratize proving and share that with every thinker, not only elite mathematicians, I think that would be a fantastic vision. And finally, to conclude, I want to say that the big ideas, they are really, really important, but maybe equally important, if not more, is the people you are doing this with, and the mindset of the team. And I think an important mindset, and here you need to have that in mathematics as well, is to be extremely optimistic. And so individually, this was almost impossible, but together, it felt impossible to fail. So this was the amazing team. So thank you very much for inviting me and for listening, and I'll be happy to take any questions.
Great talk, Thomas. Thanks very much. I couldn't resist, since you brought up this question of interestingness in mathematics. I gave a talk on there is interesting work out there, and there is both subjective and objective components. And I sent a link to a talk I've given about the topic. So it might be interesting to discuss that another time. Why don't I open it up to questions? I have questions too, but if the audience has questions, please. Any questions out there?
I have.
Okay, yes.
So I was just wondering, I mean, so if the goal is one particular goal is to discover new areas of math, very often, it's people just at the start of like the discovery of new area, people are very loose with rigor. And for example, calculus initially was far from rigorous, but people still make progress. But if like the idea is to kind of just do this like tedious step-by-step check, it seems unlikely to like come up with like to follow that pattern. So I was just wondering if there's any way to like precisely allow for like such, looseness that mimics like the discovery of like real math.
Thank you. It's a really, really good question. Yeah, indeed, I think a lot of the beginnings are quite fuzzy, and I don't have a great answer for you yet. I think that one thing that is pretty clear is that until now we've worked completely in formal mathematics, and I think it's important that we keep it to ground whatever we are doing. But nothing stops us from leveraging kind of the big improvements that's been in kind of natural language reasoning, and maybe do like part of kind of more fuzzy reasoning in natural language or any other way of reasoning. And in the end, kind of ground it in formal language. But I think that like kind of I imagine that for machines, it would be much faster to iterate on kind of theories. And it's like not very costly to kind of write down kind of a wrong theory and kind of correct it, etc., etc. But I have a lot to learn there. And I get your point, yes.
Thanks.
Christian Testa, would you like to ask your question?
Sure. Yeah, it's fairly clear to me how you would formalize the statements that came in the Math Olympiad, like prove that blank. But for statements that came in the form that you pointed out, find all x such that blank, how did you formalize those? Or was it that you had Gemini come up with candidate solutions that you then formalized? I'm just imagining that what you can give in lean code is kind of like an unproven theorem statement.
Yes, you're exactly right. So like the way that it would be formalized is you would write, for instance, in this particular case, find all x such that you write like the set of x that satisfy this property equal, and then you have like kind of a placeholder there. We had like this answer story kind of a way to code this. And then basically we'd ask Gemini to say, oh, what are all of those? And we say, well, it's actually just the set of primes, for instance. And then we'd actually auto-formalize that. And we'd auto-formalize the answer into that placeholder. And so that was like, very reliable. So we didn't have any issues there.
All questions? Let me ask you, you talk about there's a training and then there's a test time RL stage, and you take many modified or, different, formalizations of problems. Is there a success rate at that stage, broader than the IMO that you can quote?
Do you mean on a different benchmark? Or
Yeah.
different...
Well, so you, I mean, there are many benchmarks, but you implicitly have one in that you've formalized many variants of old IMO problems. I mean, is it 100%, or is there a success rate for that set of problems?
Yeah. So yes, it's it's like, so we were tracking kind of what was our performance on the historical IMOs, so that we had like kind of a good idea of what we would do at the 2024 IMO. And of course, you have to be very careful there, because you don't want to leak the data, etc., especially if you really want to participate at the competition. And so we knew that the kind of test time RL was scaling pretty well. We didn't use kind of, it was not human written variance. This was all kind of, variance that kind of the model would kind of propose.
Right.
Based on, for instance, few shot prompting or these kind of techniques. And so,
Right.
you maybe show a little bit how you do the variance with few shot prompting, but then the model would do it, right? And so basically when the model generated interesting variance, then, I guess, like the interpretation, like we solve many more problems with test time RL that we can without. And we think that the ones where we still don't make progress is that, maybe either kind of the model generates variants that are still too hard and they're not kind of close to where your agent can do, or it generates variants that are actually uninteresting. And so the vast majority of the variants are actually uninteresting. And so you need to mine kind of the interesting ones. And my guess is that actually you don't need that many. Like if you had a method that was really powerful about kind of coming up exactly with the ones you needed, you wouldn't need that many. Of course, like if I'm talking about the Riemann hypothesis, maybe you would need many. But for for the level of where our agent was versus kind of the difficulty of the IMO problems, it was mostly about finding the right chain of variance. But I think that makes a lot of sense. So there are still a lot of problems that are hard to solve. Maybe because we don't really understand how to generate those variances. That's kind of a very good thing to do in the future, especially if we want to contribute to research math, is that, well, for problems that no one knows how to solve, right? Like, how do you come up with the right ideas?
Okay. So just if I understand, so the model did solve some fraction, but certainly not 100% of the variance produced by the formalizer. But that's, in a sense, a hard number to calibrate, because there can be many variant problems which are too hard to solve or really can't be solved, and so that has to be factored out. And so it raises another question of, can one train a model to predict how hard a problem is to solve?
Yes, yeah, that would be a great thing to have, yes. So that's a little bit what you can do with value functions in R. Yeah, it's an ongoing topic of research.
I see. Okay. More questions? Well, let's see. So, do you see a path forward? So yeah, obviously, a lot of mathematicians would love to have a auto formalizer or a proof assistant for research level lean. Do you see a path forward? It just requires lots of work, or do you think there are unsolved challenges in making that happen?
No, I really see a path forward. I think we are not far away from that. And maybe like trying to get everything perfect would be kind of the wrong way to go after it. Auto formalization is really hard, and maybe I think you hear a lot of people in AI saying that verifying things is much easier than generating things. But at least from our experience, verifying auto-formalization seems to be as hard as generating the auto-formalization, at least for a human. The process of verifying is almost the same as the process of generating. But in fact, it doesn't really, to train a perfect auto-formalization is really hard. It's like a really hard reasoning task. It just looks like translation, but actually you need to get many details right. And you have very little feedback. How do you know that you've actually translated the thing correctly? There is not as clear feedback as we have for proving. But I think it actually doesn't matter. We could, I've understood this recently, is that we would want to have an auto-formalizer that that doesn't necessarily target like the experts in Lean, those who've already spent thousands of hours in Lean, but maybe for those who are interested in getting into Lean and it's like, oh, I don't even know how to express this thing, and if you have like a first guess, then it might save you a lot of time. And actually, when you're going to write the proof, that's where you're going to figure out that actually your auto-formalization has a minor problem. For instance, you might have forgotten to say that it has to be strictly bigger than 0, and then like you say, oh, but then it's actually false if I use 0 or something like this. And so like as you work on the proof, you're going to kind of refine your auto-formalization, and that's how it actually works for humans as well. And for the proving part as well, I think that it might very well be that already AlphaProof in its current status could do, proving some kind of small lemmas here and there and kind of helping the process of formalization. And so obviously, one great quality of AlphaProof is that it can scale a lot with compute, but you would want to maybe have something that is already very good with a limited amount of compute. And so, I think there is a bit of work in kind of making sure that what is the experience of waiting for 5 minutes for the prover to come back? Because it cannot do anything very interesting in 1 second, but it can do a lot of things in 5 minutes. And it doesn't need like 3 days actually. For most of the things, it could do a lot of things in 5 minutes, and especially if it's in an interactive mode where like maybe the human just said, okay, maybe I think this can be done in 5 minutes, and then AlphaProof tries, doesn't work. Then you may write kind of a simpler, you kind of add a step to your proof and say, okay, now, okay, here's a hint, let's just prove half of what I wanted you to prove first. And then maybe it will fill in that proof. And you could imagine that kind of a co-adaptation between the human and the tool, such that the tool is used where it's actually capable of doing things. And I think what we don't know is what really it is capable of, because it's not like we are testing it on all of mathematics internally now. And so I think that would be a really interesting thing and something we should do. And it's like there's a lot of hoops to jump through, but I definitely see a path forward, and that's something we'd really like to do. Yes.
Thanks. There's a question in the chat, but let me just ask the kind of evident follow-up, which is that some groups have offered lean AI tactics that say call a language model or you call a server someplace else? And do you consider offering such a tactic?
Yeah, so I think what we would offer is like kind of a whole completion of a proof, I think.
Okay.
You know, whole completion of a subgoal. So, you know, like
Okay.
you
Okay.
may
I
be
mean,
in
that
the
would be
middle of your proof and you define your little lemma there, right?
right.
And then it would not only kind of, so I don't know what is the right, the reality is I don't really know what is the most useful version of the tool. Could be I just propose you a tactic, and that could be very fast, right? That's the advantage that it would be extremely fast. So maybe, you know, maybe that's not very useful. But if I, you know, think for 5 minutes and I return you like 20 lines of proof that compiles, maybe that's a more useful kind of a more useful tool. And so that's something we want to a little bit kind of engage with the community and try to calibrate where is the most useful thing. Is it something that returns within 1 second? Is it something that takes 5 minutes? Or actually maybe is it something that, you know, would run completely offline for 2 days over the weekend? You know, you'd kind of more like kind of an was it a mass overflow or mass exchange kind of thing where you'd write your question and then, you know, asynchronously AlphaProof would go and try to answer your questions, and when it can, it would just post a reply. And then, you know, you are not expecting an answer anytime soon. You will go to bed, you will think about other things, but maybe at some point it comes back. And so at this stage, I don't know what is the most useful version of this tool. And that's something I'd love to be able to explore.
Oh, great. Well, we all look forward to seeing such tools. So there's a question in the chat, Hua Jianxing. Would you like to ask it?
Yes, thank you. And could you hear me more details about the search process? For example, how large was the search tree and how much computation power did it require? And about other details, could it be shared?
I didn't quite get the very end, but I got the first part of the question, so let me try to answer that. So, you know, like search, well, at least, you know, this is my observation that everything scales log linearly. And so, you know, you see a lot of progress with at the beginning, and then after that, you get kind of log linear gains. And so what you want is to find kind of different ways of scaling, and search definitely gives you a way to scale. So I think we see a lot of, you know, of gains of, you know, searching for minutes and hours if we want to. And so we can scale that as much as we want. But you know, the search by itself after maybe hours of searching would be really diminishing returns. So we would never really run that. And kind of the thing that, you know, scales much better when you have a lot of compute is this test time error, when you start to modify the network based on things you've learned. And so, you know, like if you don't modify your network and you do a Monte Carlo tree search, then, you know, kind of say, you know, up to an hour of search is quite effective, and you solve many more problems. But beyond that, you know, kind of trying to, what we've observed is trying to modify the wells and to adapt the network to the problem you really care about is more efficient. Yeah, and I hope we'll be able to share more details in the upcoming kind of paper.
Okay, thanks.
Hand raised from Jolene.
Hi. Thank you so much for the talk. My question is very simple. Like, I think you mentioned the MathLab is currently not like covering all of the problem. I was wondering how would you look forward to the future landscape when MathLab is like more capable of covering all aspects of the current math. So I was just wondering how would you see people interacting with maybe Lean and like the AlphaProof, like would you think AlphaProof were capable to prove more efficiently, or like how would you see the future landscape?
Yeah, so in terms of the efficiency, you know, I have no doubt that, you know, AlphaProof will become way more efficient. It's like kind of the trend you see in AI at the moment. Maybe I can't remember exactly, but basically GPT-4 has become, you know, for the same performance, you can do it with 1,000x less compute now. And so, you know, like you are making gains like very quickly. And I think that's kind of touching kind of AI, you know, that's kind of something we've seen going from AlphaGo to AlphaGo Zero. Maybe AlphaGo took us a year to train it, and AlphaGo Zero, you know, could beat that performance in 2 days of training. And I think we'll see something very similar. in the sense where, once you know how to, what is the recipe that works, to make it more, efficient is much easier. And so, yeah, I see that, I believe that, kind of AlphaProof, given minutes of thinking time, could already do something very useful for research math. Maybe not now, but in the future, especially when kind of as the coverage of math lib increases, then we can kind of tackle more and more interesting problems. Hopefully at some point where, we can become like a little assistant to researchers and kind of start to do autonomously a little bit of math and maybe more and more as AlphaProof gets better and has a better handle of the domains. I think Lean itself also would be like very good for areas of math that are like more abstract. I think Alex Kantorovich was actually describing me like what it takes for him to kind of get back into his normal work. It's like it takes him hours to load back kind of the state of where he was in the proof and how the objects move, etc., etc. And imagine it's because it's like fairly abstract. And instead, if you could kind of just load that up all in Lean, just move the things easily and see how they move, and like does that make sense? Then it could really be revolutionary. Unfortunately, these are exactly the areas of math that are inaccessible at the moment because you need to build so much before you get there. But yeah, my vision is that hopefully we can accelerate that movement and that we can contribute to more and more areas of math without infinite amount of compute. I think like kind of for interesting problems, we would want to really spend compute if we can, especially if we have a way to scale it. We shouldn't expect to be able to solve really kind of interesting problems in 5 minutes. But I think there is a very interesting talk actually by Akshay Venkatesh, who is thinking a little bit about, and that was before AlphaProof, thinking about what if you had an AlphaZero for mathematics, which is, I discovered that much later, but they were saying that, if you had something that could solve small lemmas, that would already completely change the way we do mathematics from a human perspective. So yeah, if you're interested, I think that's kind of a good talk to look at.
Thank you so much.
Any more questions?
Hi, Thomas. Really impressive work. I'm thinking about one thing. Is the MCTS search, the internal MCTS search tree really necessary? Because in my opinion, unlike Go, where when you use MCTS search, you can almost instantly get some positive rewards. I think in this math lean search problem, your policies most of the time your policy will give you no positive rewards. So I was wondering if the reward is that sparse, whether using MCTS search is still necessary, whether you can just use like plain RL algorithms like PPO or whatever to do it.
Yeah, thank you for your question. So let me respond to your first argument about Go. It's like actually in Go you also have 0 reward while you are playing Go, and you only get 1 when the game is finished. And kind of where and so and the game is fairly long, right? It's like maybe 300 moves in front of you, and so the MCTS tree will never reach the end of the game for most of the game, especially at the beginning of the game. But instead, kind of the signal it's basing its search on is what the neural network thinks are the good actions. So that's the prior, that's great, but also kind of a learned value function. How likely it is that I'm going to win from that position. And from that perspective, actually, there is no difference, I think, between Go and proving a theorem. You could train something that tells you what is my probability of proving the theorem from that state given my policy. And that's an additional signal to the policy. And then the MCTS tree search should be as good in theorem proving in Go. That said, I think it's an empirical question whether kind of the MCTS ultimately will be kind of part of the solution. I think we have this feeling from the AlphaZero Go days that the particular kind of version of MCTS we have is quite impressive. It's very hard to beat, but it's I think it's not learned to start with. It's and so like would that exact version be part of the final solution? I doubt it. But there might be some ideas that are still interesting, like you want to focus the compute on the paths that you think are the most interesting. Allows you to do kind of some parallelism, leverage parallelism in compute, etc., etc. So there are some advantages there that maybe at the moment are maybe too soon to throw away, but who knows in the end.
All right, thank you.
Any more questions? If not, well, let's thank Thomas for really very impressive work and a great talk describing it. And thanks very much. So next week we'll be having, I believe, an in-person talk by Michael Albergo, who I believe will speak about diffusion models and their theory. So I look forward to seeing you all next week. Thanks again, everybody, for coming. Thanks again, Thomas. I will get a chance to discuss further in the future. And that's all. Thank you.
Thank you for having me. Thank you.
Sure.
Bye.
Sure. Bye.